Okay, so the last thing we want to talk about is about resistance measurement. We talked about voltage and current measurement, so let's talk about resistance measurement as well. So you might think that, well, if I want to measure resistance, if I just have a resistor in the lab and I want to know what is the resistance of it, well, you don't have to go through a lot of stuff. You just need to actually apply, basically, let's say you apply a big voltage across it. Doesn't have to be big, a known voltage across it. So let's say you put a 10 volt here, and then you put an ammeter here and back to the voltage source. So this is Rx that we don't know what it is, right? So all you need to do is to read the ammeter output, and then, well, Rx is going to be the 10 volt that you know divided by the current from the ammeter. And then you have the resistance, right? The problem is that, well, if you have the resistance in the circuit, then if it's not an isolated resistance, things are not going to be that easy anymore. What would be the example of that? Well, one simple and yet, well, interesting example in the medical device kind of a field is that if you want to basically measure the blood pressure, what people use is something called a MEMS, microelectromechanical system based sensor, that basically they put something that has basically a little bit of MEMS device. It's a micro scale device that with the blood pressure, it changes mechanically, it moves mechanically. The mechanical properties of the device, the little micro device will move a little bit, and because of that, the resistance of that little piece of sensor is going to change. And now you want to actually, that resistance, that sensor is connected to the rest of your circuit. So you can't just take that out and measure that. So you want to make sure that you want to actually, if you want to measure that resistance, you have to do it while it is connected to the rest of your circuit, right? So the question is here is that, how do I measure resistance while it is connected to the rest of my circuit? How do I measure the resistance between two nodes? Let's say that I define here is A and B. Well, let's define this C and D. If I want to measure the resistance between node B and node D, the Rx as I indicated here, right? If I want to measure that resistance while it is connected to the rest of things, how do I do that? Okay. So the way that we are going to do it is something using a circuit called Wheatstone bridge. It's a very well-known circuit in electronics and instrumentation. It's useful to measure resistances. So for resistances in the range of 1 ohm to 1 mega ohm. Anything smaller than 1 ohm, it's going to be basically, we're getting to the domain of ideal wire resistance, so it's going to be tricky. We need different kind of circuits. Anything larger than 1 mega ohm, again, we're looking at different kind of leakages, so again, it needs its own circuits. But then for medium range resistances, this is actually pretty useful, and it's basically most of the circuits, most of resistors that we want to measure is in this range. So it's actually quite useful circuit. Before getting into like basically analyzing the circuit and explaining how it works, one thing I want to actually remind you, it's nothing new, but it's actually a good observation. If you have a resistor, Ohm's law tells me that if the resistance is R and I have a current I and the voltage across it is V, I know that V is equal to RI, nothing new, right? But if somehow magically somebody tells me that I is equal to 0, then what do I know about the V? Well, from this expression here, from this equation, if I is equal to 0, therefore V is equal to 0, because R cannot be 0. If I know that R is not 0, if R is a finite value, then if you have a resistor and the 2 points of this resistor, if you have a resistor and somehow you know that there's no current guaranteed, there's no current passing through this resistor, then you should be able to tell that the two nodes of basically the two terminals of this resistors are actually shorted together, or they're connected together. One example of that would be let's say I had a resistor connected to this point of my circuit, and on the other side, it's just floating. It's not connected to anything. Then I know that there's no current. So I here is 0. If I know that the current is 0, then if this is point C, as I defined up there, here is going to be also point C. It's one of those weird things that it's not really intuitive. It's not something that you expect, because you think that there's an element between these 2 points, between here and here, so they can't be the same node. But then because I know that there's no current passing through this resistor, then, well, Ohm's law tells me that the voltage difference between this point in the circuit and this point in the circuit should be 0. Therefore, they are the same node. Okay, so this is a very interesting observation. We're going to use that in analyzing the circuit. Okay, so let me erase this part so that we keep the focus on the circuit at hand. Let me write this as D. Okay, now let us assume that in the beginning we're going to start with an assumption. Let's assume that the amp meter shows a 0 ampere current. So the ammeter, the current measurement, is showing us that there's no current passing, no current flowing from point A to point B. Okay, knowing that, we know that the ammeter, we'd like it to have a 0 ohm resistance, but then we know that it has some finite, even like 0.1 ohm, but it has some finite resistance. If it has a current of 0 ohm, then the first thing we can say about this is that, number one, VA is equal to VB. So the potential of point A and point B are the same, or better way of writing this is that VA minus VB is equal to 0. Okay, so there's no potential difference between the two, right? The conclusion, the second conclusion we can take from the assumption that we made is that I1 is equal to I3 and I2 is equal to IX. Why? Well, looking at this, I can see that, well, I1 is coming here. Let's call this guy, well, we have already called it IG, right? So I know that I1 is coming in and IG and I3 are going out, but now we know that IG is equal to 0. So this is the assumption, IG is equal to 0. The current that the ammeter is reading for us is 0. So if this is 0, then I1 is equal to I3. Similarly, if I write KCL on the other at node B, I can see that I2 is equal to, I2 plus IG, because both of them are coming to the node, is equal to IX that is going out of the node. Again, because this is 0, I2 is equal to IX. Okay. Now, from these, I can write another set of deductions. So the first thing I want to say is that, okay, knowing that VA and VB are equal, so this point and this point have the same potential, then the voltage across this R1 and the voltage across R2 are going to be the same, because one end is connected to the same node, the other end is connected to a node that have to two nodes that have the same potential. So I'm going to have the same voltage drop. So VR1 is equal to VR2. Similarly, I can say the same thing about VR3 and VRX, right? So I would know that VR1 is equal to VR2. Therefore, I1 R1 is equal to I2 R2. And from here, I can say R3 I3 is equal to Rx Ix, right? Now, from these equations here, I can replace this with, I can replace I3 with I1. So R3 I1 is equal to Rx times, instead of Ix, I'm going to put I2. And then from here, I'm just going to rewrite it. So R1 I1 is equal to R2 I2. Now, from these two equations, I can say that I1 over I2 is equal to R2 over R1, right? And it's also equal to Rx over R3. Therefore, Rx is going to be equal to R3 times R2 over R1. Okay, so let me just take this out. Okay, so what does this tell me? It tells me that if I assume that if at any point if my circuit, if my amp meter gives me a reading of 0 amps, then my Rx is actually equal to R3 times R2 divided by R1, right? So how do I take advantage of this? How do I leverage this knowledge? Well, imagine that R3 is a variable resistor, right? We have resistors that basically we call them potentiometers, or like variable resistors, that you can mechanically, using a simple screwdriver, you can rotate a little pin and then the amount of resistance will change, right? Now imagine that you go to the lab and then you have R1 and R2 as fixed resistors, but R3 is a variable resistor and Rx is the resistor that you don't know it. It's the unknown resistor that you're trying to find its value, right? Now imagine that in the beginning, when you hook up this circuit, your ammeter shows something that is not 0. Let's say it shows like half an amperes, or like 1 amperes, or whatnot, right? And then what you do is that you start changing the resistance of R3 using your screwdriver, and then, well, for like a blood pressure sensor, instead of a mechanically adjustable resistor, you can actually use a digitally adjustable resistor. So you're basically, you have a microcontroller, you have a little bit of digital controller that changes the resistance, right? But after all, like, it doesn't matter if it's manual, if it's mechanical, or it's digital, you're changing the resistance, right? Imagine you change the resistance and then you look at the current. If you see that the current is actually increasing, well, change it the other way. If you were increasing the resistance, well, now let's decrease it, right? You change the resistance until the current that you read from the ammeter becomes 0. At that moment, you know the resistance of R1 and R2 and R3, and at that moment you can actually say that because the ammeter's current reading became 0, my Rx is equal to R3, the current value of R3, the variable resistor, times R2 divided by R1. And that's how you do resistance measurement. Okay, so that kind of brings all of our discussions of chapter 3 to an end. I hope everything was clear. Same as always, if you had any questions, you can ask through the Q&A feature of the Echo 360. You can add a comment, ask your question. You can even I basically indicate what exact minute and second of the video you're asking the question from, and I'll try to get back to you with an answer as quick as possible. You also have the option of emailing me. You have the option of booking an appointment with my office hour during my office hour times, or booking an appointment with the TAs. Thank you.